very good day and warm welcome to all participants to this webinar event. My name is Kanindra and I'd like to thank everyone for joining us for this IEEE PES Malaysia webinar event. IEEE PES is a non-profit organization which gathers members who has power and energy related background. With the objective to create a platform for exchange of ideas and knowledge, IEEE PES Malaysia chapter has managed to sustain its activity which would span from knowledge networking, industrial visits, distinguished lecture series, and technical conferences. Today, we have our distinguished speaker, Dr. Ahmed Fahim Zuba from Brunel University London to deliver his lecture titled Electrical Energy Storage Roles in the Future Grids. Our moderator for this event will be Associate Professor, Engineer Dr. Ahmad Farid Abidin, IEEE PES Committee member. Right before we begin our event, here's a short clip on IEEE Power and Energy Society. With that, I would like to also take this opportunity to invite all of you participants to join us in our IEEE conferences, IEEE International Conference on Power System Technology, PowerCon 2022, and IEEE International Conference on Power and Energy, PCON 2022, to be held later this year. With that, we would like to begin our event. I would like to pass the session to our moderator, Dr. Ahmad Farid Abidin. Thank you.
Okay, thank you and very good evening, Dr. Kandra, and also our guest speaker, Dr. Ahmad Zoba. First of all, I would like to thank all the participants who joins our series of webinar today, and also I would like to appreciate our gratitude to our speaker, Dr. Ahmad Zoba, for give feel give his time to share the talk or the research that he have conducted in his area. So before I would like to call our speaker, please allow me to read or introduce our speaker, Dr. Ahmad Zuba. So Dr. Ahmad Fahim Zuba received his Bachelor Science Honours and Master Science and PhD degrees in Electrical Power and Machine from Cairo University, Egypt, in 1992, 1997, and 2002, respectively. He received his postgraduate certificate in academic practice from the University of Exeter, United Kingdom, in 2010, and his Doctor of Science from Brunel University, London, in 2017. He was an instructor from 1992 to 1997, a teaching assistant from 1997 to 2002, and assistant professor from 2002 to 2007 at Cairo University, Egypt. From 2007 to 2010, he was a senior lecturer in renewable energy at University of Exeter, United Kingdom. And from 2010 to 2019, he was a senior lecturer in power system at Brunel University, London, United Kingdom. Currently, he's a reader in electrical and power engineering at Brunel University, London. His main area of expertise including power quality, marine renewable energy, smart grids, energy efficiency, and lighting applications. Dr. Zuba is an executive editor for a few journals, and currently he is a senior member of IEEE and the International Solar Energy Society, the European Power Electronics and Drive Association, and IEEE Eastern Associations. Okay, Dr. Zuba, without further delay, I would like to call you to deliver your speech, the title on electrical energy storage roles in future grid. Over to you, Doctor.
Thank you so much, Dr. Farid. Thank you, Tanindra. I am honored to be hosted today by IEEE BES chapter in Malaysia to share the recent development and the up-to-date information about one of the important and hot topics for the future grid, which is electrical energy storage. The title for my talk today is Electrical Energy Storage Roles in the Future Grid. From where I am coming today, so I am based Brunel University, London, and you can see where it is on the map. Brunel is a campus-based university situated in Uxbridge, West London, founded in 1966, home for more than 15,000 students. We are now currently about 18,000 students from over 100 countries worldwide. Brunel is 25th in the top 100 under 50 years old universities. We have 3 colleges. I am based College of Engineering, Design, and Physical Sciences. Also, Brunel has 5 institutes. One of them, which I am affiliated to, is an Institute of Energy Futures. We also have a graduate school in Brunel. As an introduction to my talk, energy storage is essential to balance supply and demand at short notice. Also, energy storage can be integrated at different levels of the electricity systems, starting from the generation level, passing through transmission, distribution, and customer levels. And we can see we have different services which energy storage can offer, including arbitrage, balancing, reserve power, frequency control, investment deferral, voltage control, capacity support, peak shaving, time of use, cost management. So we can see that the electrical energy storage will play a key role in enabling the world to develop a low-carbon electricity system. This is the main topics which I will try to cover in 40 minutes, including accelerating development of renewable energy projects, the effect that solar power has on demand for utility electricity, and we can see that these 2 main topics are the drivers of the importance of the energy storage in the futures. So we can see the future roles of energy storage after, then technology overview, technical and economical comparison of the different technologies available for the energy storage, technology development, short-term, medium-term, and long-term, what is happening in the market currently and in the future, and ending my talk with the challenges which the electrical energy storage is facing for the future. Accelerating development of renewable energy project. And looking to this graph, we can see the change in electricity demand in 2020 and 2021 by region worldwide. So we can see there is some increase, normally increase in the electricity demand, but there are some challenges due to COVID we are suffering from in the previous 2 years. And here we can see the renewable electricity generation increase by technology, country, and region during 2020-2021. We can see the key player of renewable energy in the world, China, and then we can see what is happening in the United States, the European Union, and India for the different technologies, including hydro, solar PV, wind, bioenergy, and the others technologies. Here we can see the annual addition to global renewable electricity capacity, which is expected to average around 305 gigawatt per year between 2021 and 2026, reported by the International Energy Association. They are studying for three main cases, including the main case forecast and the accelerated case and the net zero scenario. One of the technologies which has fast booming for renewable energy technology is solar energy. But let us see the problems which can be created from high level of penetration of solar energy, especially the effect that solar power has on demand for utility electricity. This is a very short storage, and it is called the duck curve. And this term was coined in 2012 by California Independent System Operator. Let us see what was happened in California. In California and in 2012, you can see that the load curve is a very normal, like a camel, which is a utility. Any utility would like to see the load curve. So no problem till 2012 in California. But when they started ramping up the solar energy in 2013, things started changing, and you can see that the camel curve completely converted into duck curve. Without duck, you can see how it looks like the load curve. You can see that on the right, we have a problem that you need ramp which is 13 gigawatt in 3 hours. And on the left-hand side, there is a risk of over-generation. Just to highlight on this ramp, if you can see, this is the hourly electric load versus the demand in October 22nd of 2016. Looking to the square in red on the load curve, which is in orange, and the demand in blue, we can see that the red curve is steep rise from 5 p.m. to 6 p.m. as the sun sets, requiring some 5 gigawatt generating capacity from non-renewable sources to come online within 1 hour, which is a problem. So what is wrong with the duck curve? As we saw, we have steep tall ramps, we have over-generation and curtailment, and finally, frequency response. There are two main solutions to flatten the duck curve. The first is the interconnection, and the second is the energy storage. To conclude these two main drivers, higher levels of energy storage are required for coping with the increasing use of intermittent wind and solar electricity, plus grid flexibility and grid stability. So, the most important question raised now: what are the future rules of electrical energy storage? And this is what we hear about it now. Let us look to this slide, and you can see how the energy storage will support the grid on the different sides of the grid or the different levels of the grid, including generation, transmission, distribution, and customer. So there are 3 points of views for the future rules we need to look at. First, from the point of view of the utility. Second, from the point of view of the renewable energy sources themselves. And thirdly, from the point of view of the customer. Let us see the future rules from the point of view of the utility. Electrical energy storage can decrease the gap between daytime and nighttime, which is called time shifting. Energy storage can provide frequency control functions, and also it can be located at the end of heavily loaded line to mitigate any congestion. And these 2 issues under power quality. Thirdly, batteries installed at appropriate substations may mitigate the congestions, as we mentioned earlier, and thus help utilities to postpone or suspend the reinforcement of the network to make more efficient use of the network. Energy storage can supply stable power to consumers, especially for the isolated grids. And finally, many batteries are used for emergency supplies in case of outages. From the point of view of renewable energy sources themselves, there are 3 future rules for the energy storage. First, time shifting, and any valuable energy comes from these renewable energy sources can be effectively used by storing surplus electricity in any of the electrical energy storage systems and using it when necessary. It can also be sold when the price is high. Second rule, effective connection to grid. So energy storage can be used for time shifting to absorb solar and wind power fluctuations more cost effectively than others. Thirdly, long-term solution to duct curvature, which becomes movable piece of the puzzle. From the point of view of the consumers, we have 3 future rules for the energy storage. First, time shifting and cost savings. So with the time varying electricity prices, consumers may reduce their electricity costs by using energy storage to reduce peak power needed from the grid during the day and to buy the needed electricity at off-peak times. Secondly, sometimes energy storage to be installed as a substitute for emergency generators to operate during any outage. Thirdly, electric vehicles and mobile appliances. And we hear that the electric vehicles can help us in reducing the carbon emissions, and there is a possibility for using vehicle to home or vehicle to grid as well in the future while having what is called smart grids. So this is just to highlight on the importance of the energy storage and how it will be a key player for low carbon future power systems. Now, let us have a fast look on the technology itself. We have different forms, so starting from the mechanical energy form. And here the storage can be in form of potential energy or kinetic energy. Kinetic energy is available in flywheels, and potential energy is available in compressed air energy storage and pumped hydro energy storage. Compressed air energy storage, we can see the schematic diagram of the energy storage, and it is based on storage of energy as the elastic potential of compressed air. Any excess of energy is used to run air compressors to pump air into underground caverns or above ground storage tanks where the air is stored under pressure. Once we need this surplus of energy or extra energy, we release this compressed air to drive turbines. The turbines will drive generators to generate electricity. This is the first compressed air energy storage plant established in Germany in 1978 with a round-trip efficiency of 41 and capacity of 60 megawatt charging. What about the pumped hydro energy storage? Pumped hydro energy storage is based on pumping water from one reservoir to another at a higher elevation, often during off-peak and other low electricity demand periods. When electricity is needed, water is released from the upper reservoir through a hydroelectric turbine and collected in the lower reservoir. The largest facility under this technology we can see it is in China, called Three Gorges Dam. It consists of 32 turbines and its capacity is 22.5 gigawatt. In 2014, the dam generated 98.8 terawatt hour and had the world record. The neck-to-neck facility to Three Gorges Dam, it is called Itabo Dam, and it is in the borders of Brazil and Paraguay. It consists of 20 turbines and capacity of 14 gigawatt. In 2016, the dam generated 103.1 terawatt hour and had the world record. Talking about the pumped storage technology itself, we have the largest facility in the world, which in the Bath country in Virginia, United States. It consists of 6 turbines and a capacity of 3.003 gigawatt. And you can see on the left-hand side the 2 reservoirs having a capacity of 30 gigawatt hour stored energy as a potential energy. In Europe, we have the largest storage system in Luxembourg, and it consists of 11 turbines with a capacity of 1.3 gigawatt. You can see that the upper reservoir is an artificial construction, and the lower reservoir is connected to the river and the dam. Here in the UK, we have one station which is called Dunwork Power Station in UK. It consists of 6 turbines with a capacity of 1.728 gigawatt. It helps us to meet peak load and also it works as a short-term operating reserve. This station is primarily used for frequency response. And just let us say, for example, if we have big national event, okay, the final of the Champions League, which coming this month, so you can imagine how many kettles are on during the halftime. You are talking about 2 gigawatt. So Dunwurg power station is mainly to support these kinds of event and to support the frequency response. For the kinetic energy technology, under the mechanical energy form, we have the flywheels. And flywheels store energy in the angular momentum of a spinning mass. They are charged with a spin of a motor, while energy discharged is achieved through the same motor acting as a generator to produce electricity. And we can see the largest facility to be installed. The news till 2019 that it should be in operation, but I don't have confirmation that it is in operation or not, but it is there. It is near Paris, and it has 1 million charging cycles and retains its full capacity over its complete lifetime. Second form of energy storage is electrical energy form, and this is storage in the form of electrostatic, such as capacitors and supercapacitors. Secondly, magnetic storage, including superconducting magnetic energy storage. What about capacitors and supercapacitors? Capacitors is well-known technology to store energy in an electric field between 2 electrodes, normally metal plates, separated by an insulating material called dielectric. We have nowadays supercapacitors, which also called ultracapacitors, and this is an electric double-layer capacitor. It is an advanced capacitor operating on the same principles as a standard capacitor, but with highly porous carbon materials having a very large specific surface to increase the capacity. We have superconducting magnetic energy storage, applies the magnetic field generated inside a superconducting coil to store electrical energy, as we can see in this figure. This technology, one of the applications in the world, you can see this is Duke Energy, both new battery and ultra capacitor system to the rest in North Carolina, which we call it nowadays hybrid energy storage. So you make mix of different technologies to enjoy the major advantages of these mixed technologies. The third form of the energy storage is thermal energy form, and we have 2 options. Low temperatures, which include cryogenic energy storage, which is a developing technology using off-peak power or renewable energy sources to generate cryogenic fluid, which can then be used in a cryogenic heat engine to generate electricity. And also we have high temperature thermal energy storage. And here we have 2 classifications. Sensible heat storage system, which applies heating of medium such as steam, and hot water accumulators, graphite, concrete, molten salt, and hot rocks to store energy without phase change of the medium. And you may know that we are using molten salt as an excellent media of storage in the concentrating solar power plants. Second classification for the high temperature is latent heat system, which uses high temperature phase changing materials, including paraffin, inorganic salts, and metals to store heat. And here we can see different applications nowadays in the world. This is a gigawatt hour scale standalone storage solution by Siemens and Gamesa renewable energy companies. Also, you can see there is a new flexibility for the existing heat cycles, again by Siemens and Gamesa renewable energy, which offer energy cost reduction and ancillary services. And here another applications which will let us use thermal power station to become energy storage plants. And this is what is called a second life for power plants. And again, this is developed by Siemens and Gamesa renewable energy. Chemical energy form of the energy storage. And here we have two options. Electrochemical energy storage, which refer to conventional batteries such as lead acid, nickel cadmium, lithium ion. We have flow batteries such as vanadium redox. We have fuel cells, which most commonly used for hydrogen fuel cells. The second option is the thermochemical storage, which includes solar hydrogen, solar metal, solar ammonia, solar methane, dissociation, recombination methods. Here we can see different applications of the battery storage in the world, just to see where they are. In Chile in 2011, there is a 544 megawatt thermal power plants. They developed 20 megawatt storage unit to perform as a critical reserve capacity. And by this way, they were able to increase the power generation by this 20 megawatt storage capacity. Again, in Chile in 2009, I developed 12 megawatt storage unit to perform the standby by spinning reserve capacity. And by this way, they increase the generation by 12 megawatt. Again, in Chile in 2011, there is a 98 megawatt wind power generation, and I developed 32 megawatt grid energy storage to provide frequency regulation services. In Hawaii in 2012, 10 megawatt dynamic power resource is integrated to 21 megawatt wind park. And the dynamic range of this dynamic power resource of 20 megawatt and 45-minute storage duration designed to provide responsive reserves to keep grid frequency deviation within plus minus 0.1 hertz. In Hawaii in 2012, I developed 496 kilowatt energy storage system coupled with 2-hour runtime. And this was in a big island in Hawaii. And by this way, they reduces the renewable energy curtailment, and it is being used as spinning reserves as well. In Missouri in 2012, there was a demonstration project which include 10 kilowatt wind turbine, 20 kilowatt solar, and the multi-tier battery storage. Again, hybrid solution is better because by this technology, you can overcome on any cons of the individual technologies themselves. And currently, this system is being used to shave about 200 kilowatt. In California in 2012, the island microgrid has a peak load of 5 megawatt. I developed 1 megawatt pure wave storage system using sodium sulfate batteries was developed to reduce the air pollution emission in this island microgrid. And finally, in Canada in 2014, remote town relies on 125 kilovolt distribution feeder. I developed 1 megawatt sodium sulfur battery, make the power to this town more reliable. Oh, there is another example in California in 2012, and Gilles Onions, this is one of the biggest industries, operates advanced energy recovery system, which went in operation in 2009 to convert all of the planned daily onion waste into a combination of renewable energy and cattle feed. This system includes 200 kilowatt modules to provide 6 hours of storage during the expensive on-peak utility rate period. We heard about all of the technologies available for the energy storage. Let us compare them technically and economically. Looking to this graph, and this gives you idea about the energy density versus the power density. So, which means going to the top corner, top right corner, which means higher power and energy density. This means lower required volume. And the graph is clearly presents this because talking about technologies of the capacitors, supercapacitors, and so on. Going to the bottom left corner where you have lower energy and the power density, this means you have larger or higher volume. And normally here you can see the different technology which needs more surface area. These graphs gives us another comparison. So we can see here the rated power versus the energy for the whole, all technologies covered, plus some extra technologies which I didn't cover due to the time limitations. One of them, which is hydrogen and the synthetic natural gas, which are promising for the future technologies in the energy storage. But from this curve, we can see that if we are talking about seconds to minutes, we can see that the double layer capacitors, the supermagnetic energy storage, and the flywheel energy systems are supporting this period of time. If we are talking minutes to hours, we can see that the fuel cells energy storage systems, the flywheel energy storage system, lead acid batteries, lithium ion batteries, and sodium sulfur batteries are supporting this area. If we are looking to days and months, we can see that the hydrogen and the synthetic natural gas are promising for this period of time, which we are seeking for it nowadays. We need longer periods of storage. Talking economically, you can see the different technologies with the cost in euros per kilowatt in power and per kilowatt hour as energy. And you can see the most competitive technology is the pumped hydro storage. We have more than 120 gigawatt capacity worldwide, but again, we know there are different constraints, mainly geographical constraints for this type of technology. So not each country can install pumped hydro storage. So pumped hydro storage is already mature and will experience small cost decreases based on more efficient power station equipment and better construction techniques. Hydrogen is projected to experience rapid cost reduction as technological advancements in both production and electrifications are achieved. Battery technologies are projected to experience similar cost reduction except in the case of sodium sulfur and a few of the redox flow batteries, which may experience more rapid cost reductions. What about the technology development? We have short-term development, and this includes two main things: innovative pumped hydro, which means new generation of variable turbines, and batteries to reduce the costs. We have medium long-term technology development, and this will include advanced pumped hydro to combine variable turbines with variable pumps, and also hydrogen, which will aim for longer-term storage, more flexible systems, and integrating energy sources with chemical productions. As you can see nowadays, that we are using offshore wind, okay, to convert the seawater into hydrogen. We transport it onshore, store it, and then you can use it later with the fuel cells to generate electricity. Advanced batteries, and as you can see, we are introducing lithium ion and the nickel metal hydride, also the emergence of the electric vehicles, including the plug-in hybrid vehicles. Thermal storage, and here we can see there is next generations of compressed air storage as well as liquid air energy storage. So we will not use compressed air, we will use liquid air. And here you can see the first pilot plant in the world. It is installed here and fully operational in Birmingham. Its capacity is 350 kilowatt with a cost of 1.1 million sterling pound. And this is an indicative layout for a liquid air energy storage for 20 megawatt energy storage system. So you can see we need only area 22 times 66 meters. And the concept of the giga plant of liquid air energy storage, trying to develop 200 megawatt power plant, and its total capex is about $230 million. This may be the future of the energy storage, which is called graphene battery. This made out of graphene. It has two silos, as you can see on the right-hand side of this slide, and we store this energy as a temperature difference between the two chambers. So you can see one chamber has a temperature difference 500 centigrade, the second has minus 160 centigrade. So this technology works like a battery, but at a grid scale will provide more cheaper solution and more efficient solution. This is the list of the advantages of this graphene battery. You can see we can reach round-trip efficiency up to 80%, highly sustainable, significantly safer. Costs over 25 years are estimated to be about $50 per megawatt hour, while pumped hydro is about $65 per megawatt hour. Isotropic graphene battery, there is a comparison, you can find it online. And here at the bottom, this is what we saw before about the Basque Country pumped storage facility, which is the largest facility of the pumped hydro energy storage system in the world, with a capacity of 30 gigawatt hour equivalent capacity. We can design the two silos, as you can see in red and the blue, up to the Basque Country facility. Each silo has height of 7 meters and diameter of 8 meters, and you can have the same capacity of the Basque Country pumped storage facility in an area of 1 to 300 of the area. So again, we all as researchers, we are working for many emerging technologies, seeking for the best options for the future grid. What about the market? We have two characteristics of electricity generate the market needs of the energy storage. First, electricity is consumed at the same time as it is generated. Secondly, the places where electricity is generated are usually located far from the locations where it is consumed. And this is normally, there is a long distance between the generating point and the load center. There are major emerging market needs for the electrical energy storage, including utilizing more renewable energy and less fossil fuels, smart grids, management and control hierarchy. What are the market needs? The market needs for lowering energy costs. The market need for flexible supply. The market need for continuous supply. The market need for avoiding congestions in power grid. The market need for mobile application. And the market need for future low carbon energy systems. This is the 6 market needs for the electrical energy storage. You can see here on this graph the global cumulative energy storage installations in the world starting from 2018 up to 2040. And the key players in this game, including South Korea, Japan, United Kingdom, Australia, France, Germany, India, and the United States, China. This is another graph, gives you idea about the battery itself, because we know the most common technology in the energy storage is battery, but we hear today about the other technologies of the energy storage. So these graphs gives us an idea about the global cumulative battery storage energy capacity between 2020 up to 2050, including small-scale batteries for commercial, for residential and at the grid scale. You can see there is booming in the utility scale batteries. Finally, what are the challenges? We have technological challenges, including increasing capacities and efficiencies of existing technologies, developing new technologies, and the market deployment. We have economic challenges by reducing the prices. We have market and regulatory issues, including incentives for building of storage capacity, as well as provision of storage services. We have strategic challenges, including the development of a systematic or holistic approach to storage. To conclude my presentation, this is a very simple conclusion. I like it. A next generation smart grid without energy storage is like a computer without a hard drive, severely limited. You can enjoy my recent books on this topic, and this comprehensive work addresses current and the future rules of energy storage, prospects and the challenges in the generation, transmission, distribution, and the customer levels of the grid. It is published by IET. From here, I thank all of my co-editors, Professor Paulo Ribeiro from Brazil, Dr. Shadi Abdelalim from Egypt, and Dr. Sarah Afifi from the UK. Also, I thank all of our international contributors in this book. Thank you.
Thank you, Dr. Ahmed, for this very interesting presentation. And now for the question and answer session, Q&A session, I would invite our moderator, Dr. Ahmad Farid.
Okay. Dr. Kandra, any question from the audience?
Haven't yet. Right. But actually, Dr. Ahmad Zuba, I have a question by myself. How are the energy storage devices, how effective are they in providing frequency regulation services in power system? Can they be used effectively?
This is one of the important rules for the energy storage, that we can use the energy storage to support the frequency response. Again, the most common technology which we are using is batteries, and you can see worldwide there is an increase in the installed capacities of the energy storage for the whole utilities worldwide. So yes, for sure, one of the rules for the energy storage, it will support frequency response. Because let us say, if you have lack of generation, then you can use the energy storage straight away just to support this reduction in the frequency due to lack of demand or anything else. So yeah, for sure, one of the important rules is frequency response.
Thank you.
Okay. Do you have any question from the audience?
Haven't yet. Okay, let me see. Haven't.
I think it is in Malaysia now is 9:30, so they may be sleeping.
Yeah.
Okay. Right. That is the...
Dr. Ahmad, I have one question regarding the graph, the density, the power density and the energy density that you have presented. There is three different capacitor: ion capacitor, supercapacitor, and capacitor. I think what is different between these three capacitor? Can you describe a little bit, Dr. Ahmad?
Yeah, we know the conventional capacitors, which is just two metal plates, and in between you put the dielectric. Then you had a storage facility using the electrostatic energy. But we enhanced these traditional capacitors by having double layer capacitors. And by this way, we started to increase the capacity of the energy storage we want. So you can now have higher capacity with the same number of the capacitors at the end of the day, but using what is called double layer capacitors, or some are calling ultra capacitors, some are calling them as ultra capacitors, but at the end of the day is enhanced capacitors.
Okay, all right.
I think there is a question here.
Yeah. From Michael J. What do you think about the carbon capture and sequestration storage (CCS) technology
Yeah, this is again one
from
of
the
the
new
area.
technology?
This is one of the areas which the world is working on it, because as we all know, we have climate change, we have global warming problem, and we all working on targeting certain amount of carbon emissions. Here in the UK, we are targeting net zero by 2050. So one of the things which we can work on it and how to capture the carbon and you store it. And you can see that one of the interesting examples we are using, for the bioenergy, because bioenergy is emitting carbon emissions. But to make it green 100%, we can establish this power plant, near the more green area, trees, and all of this. So we can close the carbon cycle to get it at the end as zero carbon emission, but internally there are carbon emissions. So this is how we can capture the carbon. Very simple example. And again, how you can store it, just to reach at the end of the day, if we can reach one day to solve this issue, having zero carbon emissions. But it's not related to the electrical energy storage. Just, I think these questions is carbon capture and the storage is completely different from the energy storage.
Okay, any more question? I think we can open one more question, I guess. It's already 30, 9:30. Okay,
Yeah,
this is the last question. Recently, there has been a further interest on gravity-based storage devices. Are such technology practical and efficient for energy storage? From Gotamraj. Okay, thank you, Mr. Gotamraj.
Uh, it is there again, but the problem is many ideas are there, but what will be practically implemented is the question. But because what we are seeking for more efficient and low cost technologies. Yeah, the ideas. Let us say, for another example, just to clarify this for you, who asked these questions. Let us talk about marine renewable energy and simply ocean and the tidal energy. Okay, these technologies, if you go back 10 years ago, and I worked on one of the largest research project, 15 million pound research project on the future of marine renewable energy. Because in 2005 to 2010, we had the studies confirming that these technologies, wave and tidal, will compete the wind beyond 2020. Because we all know the wind is gorilla of renewable energy. But here we go, we are in 2022 and nothing happened. Because the problem, we as a researchers, we developed more than 500 prototypes of wave energy converters. But when you go into the market, you will find very few products available in the market. So there is fear from the manufacturers, from the decision makers to go ahead. So again, gravity storage, okay, it is there, but if you can check, there is this technology, I cannot say technology, it's this idea. Yes, it's like graphite battery. Graphite battery in 2010, they said this is the future. And we have now in the UK, okay, the first pilot project for this graphite battery. But will it go to be at the grid scale in the future? 10 years now, and we are still talking about prototypes. So to convert the ideas into a real product, there are many directions, not only the research. There is policy, decision makers, political issues, all should be taken into consideration to make the final decision, say, yes, let us go with this.
Okay, there's one more question. Is it okay, Doctor? You still have plenty of time to answer?
Oh,
This
yeah,
one,
yeah, yeah.
another question that I've been posed by me. Okay. I have a question to ask. Is Malaysia share the similar energy storage challenges with the other ASEAN country? Okay, that's number one. Number two, what are the countries with success BSS story and how is their policy regulation or incentive as compared to ASEAN countries? The third one, what is the main hindrance for BSS adoption in Asian countries and what Asian countries can learn from other countries with successful BSS adoption? And the last one, in terms of BSS research work, which area is still lacking that requires further works? Okay, that's very long questions. Consists of 4 different questions. That's it.
No, it is okay, but simply, I can, we can conclude all of these questions again in one thing. The technology is there, but you need to invest on it. And this is the difference between, the worldwide countries. There are countries, they have the investment to invest in these technologies. And you can see, as I mentioned during my presentations, there are key players in the energy storage, and especially battery is a well-established technology and number one after the pumped hydro storage. So in Asia, you can see Japan, China, South Korea are key players in this. They are installing higher amount of energy storage during the coming years. So United States, here in Europe, we are one of the leading countries, okay, for the energy storage and especially battery energy storage systems. So there is no problem, again, with which country will install. But as you mentioned in your question, there are policy issues, there are regulations to be arranged, and also incentives. And as you can see during my presentation, I mentioned one of the challenges we are facing is we need to provide incentives to build energy storage system. Okay, because you can build energy storage system in your home with a small PV system, okay, and this is back to utilities. You can see Germany is a very successful story that the majority of the homes in Germany, they have their own PV systems, okay, installed with the appropriate energy battery energy storage system. So yes, uh, there are many drivers, okay, to end with this country will include energy storage or not. Okay, some times ago here in the UK, we are dependent on the interconnections than the story, because if you have interconnection, you don't need to have energy to invest for new power plants or new infrastructure for the energy storage, because once you need power you will take from your neighbors, and any surplus of the power you have, you export it to your neighbors. So the interconnections is an alternative for the energy storage. But you can see countries have interconnections, countries no. I hope that I clarify this list of questions to you.
Okay, another question. One of the major concerns with battery technology is the pollution produced by batteries once they have reached their end of life. What is the direction of research to address the issues? This one is the what we call it, the batteries who are already reaching to the end of life cycle. So what we will do with that kind of the materials?
If you are talking about the pollution coming from the energy storage compared with a coal for, let us say, coal fuel fired power plant, you will see, So we are reducing the carbon emissions. Again, if you say, yes, battery is not green energy, because if you will talk about the life cycle analysis of the battery technology, you have carbon emissions. Yeah, let us say lead acid battery. You need to get the lead. You need during the manufacturers. You may use fossil fuels electricity. So this is the thing that at the end of the day, you don't have zero for the battery. It's not zero carbon emissions, but compared with the other technologies of the traditional technologies or the conventional power generation, no, we are green to use this energy. But with these technologies regarding the pollution itself, there are more concerns, not only the pollution. You can know the sudden death of the battery. And it's a very simple, thing that for no reason the battery did. Okay, so you need regular maintenance, and we have the different options, depending if you need less maintenance or you need longer lifetime. So it's not only pollution. Pollution is a very minor concern for this, but our concerns more than that enhance the future, increase the efficiency, and getting more enhanced technology for the future. Lithium ion is a key player now. We all know this is the number one technology, but again, we don't know the future.
Okay,
I think
I
those are
think
questions.
we can.
Yeah.
Yeah, I think that's all. We can stop because it's already 40 past 9. Okay, Prof. Dr. Ahmad Zubair.
Okay.
Thank you very much for very interesting sharing sessions. So again, I would like to thank all the participants, and over to you, Dr. Kanendra.
Right. So I'd like to take this opportunity to thank our distinguished speaker, Dr. Ahmed Zuba, for this very informative talk and knowledge sharing session through this Q&A. I'd also like to thank Associate Professor Dr. Ahmad Farid for moderating this event, and to thank all the participants for joining this event. Thank you. Till we meet again in our next webinar event. Thanks.
Thank you so much.
Okay.
Good night, all.
Thank you, Prof. All right.